This morning it looks like Blue Origin, Jeff Bezos' Blue Origin, launches a New Glenn rocket into orbit down in Florida. It looks like 2 o'clock in the morning here on the East Coast in the U.S. They did this. Cocoa Beach. They're launching this thing into space. I can remember maybe 10 years ago when Mr. Musk and SpaceX started really talking about the idea of manned spaceflight. And they put the car into orbit around the sun and all that, public relations stuff to get the public, just fantasizing about this. I remember sitting at work one day eating lunch, and we had a engineer there who said that they had a list. You could sign up to pre-register to go to Mars. And he said that, and I reflexively said, okay, you can go. I'm going to stay right here. Of course, I'm in a room with some technically minded people, and they probably looked at me like, what an idiot. Why wouldn't you want to go to Mars? Oh, man. Of course, I don't really know what they were thinking, but when I have conversations sometimes about manned spaceflight, some people may be a little bit thinking that I am contemptful of the concept, which actually I am. And let's explain why. Let's think about it. So they're using a chemical rocket here to launch people into space. We've gotten really, really good at that, right? Between SpaceX and now Blue Origin, we have chemical-fired rockets that are pretty nice machines that can be reusable, that are able to be brought back down after a launch. If we had to abort, we should be able to bring the thing back to the surface. That's impressive. But that's only the first stage of space travel. Getting out of Earth's atmosphere is hard. It's difficult. It's risky because Earth provides a lot of gravity. Gravity is not forgiving. So we need to use a lot of power to escape it. And that carries a lot of risk because you're burning oxygen with hydrogen or methane or whatever at high flow rates. And if it fails, you know what happens, right? So the situation is that this is the first step of the process. So when we talk about this right now, we're basically, if going to Mars is up here, we are here. And it's like, people will tell me, well, we have a space station. We have people in space. We've been doing this for years and years and years. I'm like, we went to the moon, for God's sakes, right? Okay. How far away is the space station from Earth, from the surface of the Earth? It's like 300 miles. Right? 300 miles or so off the surface. That's like the distance from here to Boston, Massachusetts. From Philadelphia to Boston, Massachusetts. Let's just say that's how far away the space station is. Is that space travel? You be the judge. We talk about sending people to Mars. We're talking about putting them inside of a metal tube and putting them into a flight path that lasts for something like 6 months. Anybody who's flown on an airplane, 6-hour flight is, we prefer not to do that. It's not exactly the most fun activity that ever existed. sitting in an airplane for 6 hours. Imagine sitting in one for 6 months. Of course, we all know that it would have to be designed in such a way that people can go about their everyday business, that they can do recreational activities, that they can get up and move around, they can exercise, they can be entertained, they can do whatever, you know. It would be psychologically impossible to have it any other way. People would go insane. You can only surf the web for so long. You know, and the problem you have on a trip to Mars is what's the time flight for light between Mars and the Earth? So you're going to go up there you're going to be on this spaceship, and the first couple of days it's going to be all fine and dandy. You're going to be sitting there with your Facebook and your YouTube and whatever, and oh yeah, I got internet, I got Netflix, oh, it's all great, right? Well, time goes on, time goes on, month, 2 months, 3 months, 4 months, and suddenly you click the link to watch another YouTube video, and it's like, well, it's taking some time, huh? Isn't it like an hour time flight from Mars to Earth for light? Oh no, it's only 3 and 22 minutes. So depending upon where you're at. So okay, so you push the button to click the link to go to your next web page, and it takes 22 minutes for the request to come back to Earth, and then another 22 minutes for the content to show up at your device. So you're going to wait almost an hour. It's worse than dial-up. And of course, out of all the problems that we would have, that would be the smallest. I'm using AI, look at that. So the situation then compounds to, all right, the next thing I got to do is I just drank a coffee on the flight. They did the flight attendants, or whatever we call them, come around and they provided me with a coffee in the morning on my first day in flight. What's the next thing that happens within 20 minutes or so? Uh-oh. You're looking around, where's the lavatories at on this thing? Man, I'm going to need to blow the bathroom up here, right? Coffee. You know what happens. You're in microgravity. And you got the shits. What's going to happen? You got to find the toilet. Well, they have space toilets, you know. Basically, the way they work is that it's a vacuum. It sucks the poop right out of you, you know. It has to, because the gravity can't do it. You know, they have them on the International Space Station. Hey, what's it look like? They just replaced the shitter up there. It was $23 million a few years ago. So, you know, basically you have to sit down. You got handles because you got to be able to hold. You don't want to float away from the hole, right? You do your business, and you know, flush, which it's a vacuum system, and it takes the stuff through a mechanical, engineered set of pipes and blowers and various pieces of machinery, because you don't have the benefit of using water in combination with gravity to convey the material to where it's got to be. Right? So that's your next problem. But after that happens, you know, eventually it's like, well, on the International Space Station, what do they do with the fecal matter? What do they do with the waste? Solid waste, they compress it into I think they dry it. And then they put it into a containment bag, and then it gets loaded into a disposal capsule, and it gets launched where? It goes into the big old space incinerator, which is also known as Earth's atmosphere. It all comes back to the surface. in one way or another, or it ends up being gasified and ends up in the atmosphere. Do we have that luxury on a flight to Mars? No. We have the option of jettisoning the material into interplanetary space. I guess you could do that. But what's the problem with that? Right? There's a big issue here. We're going to go to Mars. Does Mars have a resupply? Does it have a canteen? Does it have a Walmart with food and materials that we could use to replenish ourselves? Because we threw all of our carbon and all of our chemistry into space by flushing it down the commode on the way there. No, it doesn't have any of that. We can't afford to flush our stuff into space on a interplanetary space flight. We have to recycle it. So we have to basically do waste treatment on this vehicle. We have to have a full-scale waste treatment system that uses biology to transform human waste into nutrients, into biomass, because then we have to save all that material so that we can use it to grow new food. So then after your coffee, a couple hours go by, they come around, they feed you lunch. Where's the food come from? Well, we brought it from Earth, right? Well, you're going to fly for 6 months. How much food is this vehicle going to have to carry to feed all these people for 6 months? Quite a bit, right? Just think about all the groceries that you buy in your house for 6 months. It's a lot. Think about every time you use the bathroom in 6 months. There's a lot of material there. We have to maintain a ecosystem. We have to recycle all the waste. And the thing with it is most of the most of the food that you eat. So if I eat carbohydrates, we think, oh, it comes out in feces. Well, actually, it doesn't. Most of it comes out as CO2. The mass of the carbon is exhaled as carbon dioxide. And then the water that's a product of effectively combustion, of metabolism, is in urine. Some of it's in feces, some of it's in vapor from sweating and exhalation. So that carbon dioxide that we exhale, what do they do with that on the International Space Station? Well, they have a system that scrubs it out of the air. And they convert it to a stream of concentrated CO2. That's relatively easy. That's a fairly basic engineering problem. We can do that, no issues. And we take that carbon dioxide and they react it with hydrogen in a process called a Sabatier reactor. And that converts it into methane. So we basically get, actually they react it with either hydrogen or water. I don't recall. But basically you're getting water and methane as a product from H2 and CO2. The water is recycled. The methane is where all the carbon ends up. What do they do on the International Space Station? Well, they vent the methane into space because you're getting resupplied with food from Earth, and the cost benefit of reusing that methane somehow isn't there, so we just let it go. You don't have that luxury here. Disposing of the methane to outer space is equivalent to disposing of feces to outer space. So then we have to take that CO2, probably the thing that would happen is the CO2 in and of itself would be recycled into a farming operation of some sort to produce food products. That's the easiest pathway if you're growing plants or you're growing some kind of photosynthetic material. you use the carbon dioxide as a input to make that happen. But you also need energy. So let's say we have a section of this space vehicle, and it has let's get the space toilet off the screen here. We have a section of this thing, and there's a big greenhouse in there. And you put the carbon dioxide in there, and you have water. Recycling water is pretty simple. We're not worried about water. We can keep that in circulation with relatively basic technology. But you need water, you need CO2, you need nutrients. You get the nutrients from the toilet, you get the CO2 from the breath, you get the water from urine and whatever else. You get energy. You need to give these plants or algae or whatever it is light. So you need electrical energy to power the lights. Presumably, you're going to do an indoor farming operation. People know how to do that. We're very, very good at that here on Earth. Especially, take the expertise of the cannabis industry, and there you go. They contributed to the world of space flight. But then you have to get energy. Not only do you need energy for the growing the food, but you need energy to run all these toilets and water recycling and CO2 scrubbing systems. You need energy to maintain the controls. You need energy for communications. You need energy for HVAC. You need energy. Where does it come from? Well, in the International Space Station, they use solar panels. Really big solar arrays. If you look at the space station, the first thing you notice are the solar arrays. They take up a lot of area because you need to be able to capture solar radiation. What happens is you get farther and farther and farther and farther away, you end up needing more and more and more surface area to get the same quantity of power. The inverse square law, right? You go twice the distance, you need 4 times surface area to obtain the same amount of power. That becomes an issue at Mars. We think that solar power here on Earth, it works really well as long as it's not too cloudy and all that good stuff. It's a good technology. But on Mars, your solar panels need to be a lot bigger to do the same job. So then people will go to the point, well, we could use nuclear reactors instead of solar power. All right. You could. The situation then becomes you're relying upon a much more complex piece of technology. You need a lot of redundancy. You need expertise on board that spacecraft that can maintain that technology. Solar panels are easy. There's really not a lot to it. You set it up, you put it in the sun, and it just works. There's not much to fail. A nuclear reactor would take quite a bit of engineering to get the reliability necessary for a life support system. Chances are you'd have multiple of them on board, and you'd have to fuel them in such a way that they would be able to sustain this operation for years at a time. And of course, we do that with submarines, and we do that with, naval vessels, ships. But those reactors are extremely heavy. They require concentrated, enriched fuel, and that poses risks. It poses risks to the people on board because you have a compromise between shielding, because there's high energy neutrons being thrown out by this reactor, especially if it's a fast reactor that breeds its own fuel. Everybody's like, we could use breeder reactors that will make the fuel go farther. You can, but then your shielding needs to account for the fact that the neutrons are that much more penetrating. So you'd have to build the reactor way back here, and the people are way over here, and there's enough stuff in between so the people aren't getting nailed by neutrons. That's important. Not impossible, but difficult. Very difficult. And of course, you can imagine different types of power cycle. But then we got these nuclear reactors on board here, generating all this energy for the plants, generating it for the waste treatment, generating it for the communications and controls and heating and air conditioning. Air conditioning. Nuclear reactors, what do they produce? They produce heat. What is the first thing that you see when you look at a nuclear power plant? You know, what's the stereotype of a nuclear power plant, huh? What do they look like? Oh man, what's this? Look at this, look at this. What are these things? That's the thing that comes into our brain. We see this, those weird curvy things, right? In fact, those of us who are technically inclined might understand that actually has nothing to do with the fact that it's nuclear. All it is that it's just a gigantic tower to get rid of heat. And the way they do it is by boiling water and venting the vapor into the atmosphere. Can we do that in space? Can you have a cooling tower on your spaceship that the reactor dumps its waste heat into and boils out water that just wafts off into the space? Clearly that's not going to work because you're going to run out of water probably within the first day. How do we get rid of heat in space if we can't build cooling towers? We don't have an atmosphere. How does your computer or your PC get rid of heat from its processor? You know, how does that work? Doesn't it? You don't have a cooling tower in your computer, right? Most of us don't. Let's see what I have here. Oh, here we go. There's an example. This is a great example. Ha! What's this thing? A heat sink. You could bolt the processor to this, and it will heat the metal up, and the metal will get hot. And then why are all these fins on here? Well, it's surface area. And the thing gets mounted like that, and it creates a convection current. And air flows through here. Cold air comes in the bottom, and hot air goes out the top, and the air molecules take the heat away. Oh, nice, right? Can we bolt this to the side of our spaceship, and the nuclear reactor's power cycle is exhausting its heat into this thing, and it just gets vented off into space? And yeah, theoretically we can do that. But what's the problem? Think it would work? Kinda. There's no air in space. You don't have any gas. So you bolt this thing to the spaceship, it gets hot. And here on Earth, cold air would come in the bottom and hot air would rise out the top, and it would just continuously do that. And the heat would be disposed of that way. There's also another way that heat is going to be removed, and it's by infrared radiation just shooting off of this because it's a hot thing and it's going to radiate energy. So in space, where there's no gas, there's no atmosphere, the only way you have to get rid of heat is by radiation. You heat the thing up. You know? Infrared or visible light. You have to basically turn the heat into light. Right? Which we can demonstrate, you know? And the relationship between how much heat you can get rid of per unit surface area. There's a lot of surface area on that, right? The relationship is temperature to the power of 4. So you basically exponentially, basically to the power of 4, the hotter it gets. Basically, we're going to convert, maybe, this thing's junk. Oh, we're going to convert heat into light. And the hotter it gets, the more light is emitted. And the easier it is to get rid of heat. In space, that's the only option you have. So that presents us with a problem. We have to basically compromise between how much surface area hangs off the side of this spacecraft, how many fins we have, and how hot they are. See what the space station does. Because the space station has to get rid of all of its heat through radiators. Right? They're on the back of the solar panels, heat rejection system radiators. Maybe. So they got these big panels of metal, and there's fluid flowing through there, and the fluid is hot. It heats the metal up, and then the heat is turned into light, infrared light that you can't see, and it goes into space. So our nuclear reactor is providing all this energy, providing enough power to support a human ecosystem. Growing corn or sugar cane or something like that under lights. Basically an indoor marijuana farm. We know how much electricity they use. You need a system that can provide that much power. And then some, because there's people got to eat. It's not just a few grams of bud here and there. The situation then is the engineers got to find out how much radiator they need. And the hotter they decide to make it. So it's like, well, we can't make them too big. We're going to run them hotter instead. The hotter they make it, the less efficient the power cycle becomes. It's the Carnot theorem. Basically, the efficiency of conversion of heat into mechanical work is a function of the difference in temperature between their heat source, the nuclear reactor, and the radiator surface that you're dumping the heat into. On Earth, we have the luxury of using those cooling towers to basically cool the cold end of the power cycle down to, a few degrees below atmospheric temperature, the wet bulb temperature. It's pretty nice, right? Here, you're probably not going to be able to achieve that unless these things are just gigantic. And then you run into the challenge of you're going to get to Mars and you're going to hit an atmosphere and you're not going to be able to afford having all this stuff hanging off the side of the ship because it's going to cause drag and it's going to be an issue on re-entry, even in a thin atmosphere. So you're probably going to have to throw the radiators away or do something with them otherwise when you get there. How do we handle that situation? So getting rid of heat's a problem. That's a challenge on a human occupied long duration mission where the space station I think has a total of like 80 kilowatts. Maybe it's higher now. But at one time, it was 80 kilowatts of installed power, which isn't very much. That's not very much. You think of a human diet. Let's get a calculator here. Each of us needs like 2,000 calories, right? A lot of the people who I have conversations with this about, especially online, seem to have contempt for things like the traditional environmentalists and things like that. And the idea of, let's just say, veganism, eating only plant material, is probably going to conflict with the hopes, dreams, and ambitions of anybody wanting to go on these space missions. The International Space Station, they can send them meat. They can send them beef products and pork products and chicken products from Earth. If you're going to Mars, you will not have that luxury. Carnivore diet is out of the question. Let's just think about this. 2,500 calories per day per person. That means that, let's just keep it in calories. So your average plant, like, corn, let's just assume that it's 4% efficient at converting light energy into carbohydrates. That might be high. I think sugarcane is the best, 8% efficient. So 1 kilowatt hour, or 1 calorie of light hits the plant, 0.08 calories comes out as actual carbohydrates. So that is a really bad number. So you need 12 units of light to make 12 calories of light to make 1 calorie of sugar. And if it's 4%, it's double that, 20. Let's just say it's 20. 20 calories of light for 1 calorie of corn, of carbs, starch, sugar. How efficient are your lights? Converting electricity into light. How much of that light hits the plant versus how much hits the ground or hits the walls? So an LED bulb making a nice white spectrum might be 30%, 30 to 40. I don't know what it is nowadays. Back in the fluorescent days, I did this calculation. It was like 30% conversion efficiency of electricity into light. So if we just say it's 20 times 3, 60 units of electricity to make 1 unit of food, calories. Your nuclear reactor is able to convert heat into power. And let's just say that the engineers were able to achieve 30% power cycle efficiency from heat to electricity overall. That's about what we can do on Earth, with a simple cycle power system. So then you need to multiply that by 3 again. You need 180 units of energy from your nuclear reactor to give a human being 1 unit of energy. And of that 180 units, 179, well, actually all 180, have to be exhausted through these radiators, because even the body heat from the people has to be collected by air conditioning systems and pumped out into space. This is sounding like a really, really, really difficult thing to do. It sounds like there's a lot of chances for something to go wrong. And if you're 4 months out from Earth going to Mars and something fails and there's a part that breaks, there's no option to get a new one. You can't just call AAA and they send a tow truck out there to change a tire or whatever the part is. If the ship breaks down and loses power, or a critical heat, say this heat rejection system springs a leak, and vents all of your coolant into space, that's an issue. So you got to have redundancy on top of redundancy on top of redundancy. Because if one system fails, you need to have a way to back it up and keep everything running to enough of a level to keep people from going insane and killing each other. Literally. I mean, if you lose so much power that you can't sustain anything other than basic life support functions, that's a big problem. It might be fine to do that on a naval submarine. Okay, the guys can survive for a few days under duress. But here, that's not a practical option. People will go nuts, and there will be disorder and chaos among the people occupying this vehicle. And I'm saying all this stuff before you even reach the top of Mars' atmosphere. Once you get there, then you have to do all this stuff again on the surface and sustain it. You basically have to build all these life support systems. Hopefully the vehicle that you have, you're able to just land it somehow and use all the equipment that's on board, because otherwise you have no choice but to there's nothing else there. You have nothing there. You have to use what you bring with you. If something happens and you lose a bunch of a critical substance like water or oxygen, or the thing springs a leak and you can't get it fixed and your atmosphere is venting into space and you're losing all of your gases, your O2 and carbon dioxide, nitrogen if there is any, there's no recourse. You can't just go have Air Products bring you up a bottle of oxygen to replace it. Maybe when you get to Mars, you can dig up the rocks, or maybe you could take the CO2 out of the atmosphere on Mars and crack it and make oxygen that way. But that's only once you get there. You have to have some kind of system in place to do that. What if a disease comes through your farming operation? Right? Because we're relying on biology. You have to rely on biology because human beings need a diet that is going to sustain them and keep them healthy. We have biology in the waste treatment system. We have biology in the farming or food production areas. We might have fermentation. We might have various ways of producing things that are not typically used on Earth. How do we get medicines? Like if somebody needs a particular drug, you have to manufacture that somehow. What if somebody gets sick? What do you do? What if somebody dies? What do you do? Do you just jettison them into space? And you can't do that. You don't have a crematorium up there where you can just turn them into gas like we do on Earth. What do you do? These are all questions that I don't think that we've been asking ourselves when we talk about the fantasy of going into space. And this is why every time somebody says, oh man, we're going to go to Mars, I'm just like, you can go. I'm going to stay right here. How about radiation from the sun, from interstellar space? Here on Earth, we have the luxury of an atmosphere. Once again, I keep bringing up this atmosphere. It shields us from cosmic rays. It shields us from solar particles. It shields us from ultraviolet light. It shields us from all sorts of really nasty things like micrometeors that burn up in the atmosphere and never hit the surface. It serves as a place for us to dispose of unwanted gases. We take it for granted. We drive our car down the street, and where does the gasoline go that we burn? It just disappears, It goes in the atmosphere. That's the entire crux of this climate change problem. We keep pumping waste into the atmosphere. And the natural ecology of the planet does not remove it faster than we put it in. You know, we just use the atmosphere as a dumping ground for our unwanted stuff. I mentioned many examples of that. We don't have that luxury here. About the oceans. We use the ocean. You know, waste treatment, like dealing with sewage. It's never 100% effective. You don't ever get 100% destruction and removal efficiency in any kind of pollution control system. It's very, very, very difficult to get really, really high efficiencies. So your town's sewage treatment plant might remove 90 to 95% of the stuff. Where's the other 5% go? It goes into the receiving waterway, and nature takes care of it. The biology and chemistry in the waterways, through processes as simple as dilution, all the way up to just, you know, bacteria and chemical weathering and neutralizing with rocks and minerals, interaction with atmospheric gases like CO2, all helps to eliminate those things. But we have to think about that when we start putting people into artificial environments and sending them outside the bounds of the earth. It's an inhospitable environment. It's not a place that would be pleasant to go. But as much as it sounds cool, it sounds like the airplane flight from hell, in my opinion. What's going to happen to you in microgravity? I mean, we have data from that from the space station. We have people that are up there for months and months at a time, and they have to exercise or their bodies will atrophy. So gravity on Earth is important. The atmosphere is important. The biology that's all around us. In our guts, where there's all these sayings about how many bacterial cells every person has in their body. And those bacteria are producing chemicals from our food that make it easier for us to absorb nutrients. It's a symbiotic relationship. You know, there's the old experiment where you put sugar water on your hand and you let it dry. And within minutes, the sugar is gone because it was consumed by bacteria that are on your skin. There's bacteria everywhere. There's microorganisms all over the place, and we take them all for granted. And we go up here, if that stuff is changed or missing, what's the effect? So that's a challenge in a really big way. I think I've covered enough. It's a lot of time. But there's a lot to think about when we talk about space travel. It's a very, very, very complex situation. And when these guys in the tech world act like it's going to happen tomorrow or in 10 years or 50 years, I don't think we've asked all the questions of the engineering of such a project. Going to the moon for 3 days and eating out of MREs and plastic bags, okay, we can do that. Pissing into bottles, all right. Going to Mars for months and months, and are you going to come back? Do we have a return trip to Earth? Can we swing a return flight? I don't know. That's a question to be asked. Who wants to go on a one-way trip? That's a frightening concept. At least for me it would be. You have all those risks that you're taking doing that. So those are the technical issues with the situation. That's about it for now.